This video cast is about shorthand notation for electron configuration. As you've seen, they get kind of long, and there has to be a shorthand, so I'm going to show you that. We'll also talk about how to write the electron configuration for ions and some exceptions to the Aufbau principle. So we'll start with the shorthand. Abbreviated electron configuration is called noble gas notation. Make sure that you know that this is what it's called. When I ask for it on a test, I'm going to be expecting noble gas notation back. So you've got to know what it is. And what you're going to do is, when you write this type of electron configuration, you're going to start with the preceding noble gas. Remember, noble gases are those elements that belong in group 18. So what I mean by preceding, so if we're going to write an electron configuration this way for sulfur, we look at the periodic table and we want them in numeric order according to the blue number or that atomic number at the top. So the one numerically, the noble gas out of group 18 that comes before sulfur. So sulfur is number 16, so the preceding noble gas is neon, and that's what we would start with when we're looking at our electron configuration. So the abbreviated, if we look at sulfur and just write its electron configuration, it's 1s2, 2s2, 2p6, 3s2, and 3p4. Well, what that looks like on an abbreviated is we're going to take, so this is the abbreviated one, the noble gas notation. So we'll have sulfur, and we will start with square brackets, and we put the preceding noble gas in square brackets. It has to be square brackets, it cannot be parentheses, and the element that you put in here has to be a noble gas, something from group 18 on the periodic table. Then you're just going to pick up where neon left off. So this part right here just says whatever the electron configuration for neon is, and then we build onto that. So after neon, if you look at your periodic table, and we're going to write electron configuration starting from after neon. So we'll start at sodium. We're at 3s2, and then it would be 3p4. And if you look at the longhand version, this part right here, that is the electron configuration for neon. And so we just have to add that part as far as the shorthand notation goes. All right, I've done a few of these. You ready? So, there's the sulfur example. Here's another one. We have magnesium. And again, magnesium's preceding noble gas is neon. And then we build from there. And so it would just be 3s2. After neon, we just have to do 3s2 to get to magnesium. You can try to do iron and write the abbreviated or the noble gas notation for iron. So pause the podcast or video cast and try that one out. Okay, the preceding noble gas for iron is going to be argon. Iron's number 26, and the one in numerical order that comes, the noble gas that comes before that is argon at number 18. All right, and then after argon, with our electron configuration, looking at your periodic table, it would be 4s2. And then we get to the D block. Remember, we have that little trick with the D block. It's going to be 3d, and then we count over to iron, and that would be 6. And that is the noble gas notation for iron. All right. Now remember that my purpose is to teach you how to do electron configuration, both longhand and shorthand. So the deal is you have to write them out in the complete electron configuration unless I specifically ask for the noble gas notation. Then you can write the abbreviated electron configuration. On your test, you will be tested with both. I will ask for the complete electron configuration on some, and some I will ask for the noble gas notation. Now we're going to talk about writing the electron configuration of ions. When ions have gained or lost electrons, so in our electron configuration, we must show those electrons that are lost or gained. we look at sulfur, sulfur's electron configuration is right here at the top. There we go. And just writing it as it appears. So when sulfur becomes an ion, it likes to develop a 2 negative charge. Now with that 2 negative charge, has it lost or gained electrons? It has gained electrons, because remember electrons are negative and it has 2 more of those. So our electron configuration must show those 2 extra electrons that this atom has now gained. They're going to follow the off-ball principle, so they're going to enter the lowest energy orbital that can receive it. All of these are full, every single one. This 3p4 is not full, so we're going to add these 2 electrons onto that, and that is going to make the electron configuration for this ion to be 3s2 and then 3p6. I've just added 2 to the 4 that were already there. Now, this is no longer, if you look at the periodic table, this is the electron configuration of argon. Argon is a noble gas. Noble gases are stable, and that is a common thread throughout chemistry, that atoms are trying to become more stable. So if sulfur can get its electron configuration to look like argon by gaining 2 electrons, that's what it's going to do. And sulfur will often like to gain 2 electrons. Now, when electrons are removed, they're always removed from the outer energy level. And that's important to remember. If we look at magnesium, which is the second one up here, magnesium's electron configuration is 1s2, 2s2, 2p6, 3s2. When magnesium becomes an ion, it likes to become an ion that is 2 positive. Because this charge right here is positive, that means it has lost 2 of those negative electrons. So what's going to happen is 2 electrons are going to be removed from this electron configuration. And the 2 that will be removed from the outer energy level. The big numbers tell you the energy level, so we go to the highest number there, because that would be our outer energy level. And these 2 electrons that are in the s sublevel are the ones that are going to be removed. So the electron configuration for magnesium is 1s2, 2s2, 2p6. Now, that is the electron configuration for neon, another noble gas. And so magnesium, if it can attain this electron configuration, it is a more stable atom and is going to prefer to be that way. Now, exceptions to the off-ball principle. The off-ball principle says that electrons are lazy. They don't want to have to exert any more energy than absolutely necessary. So they're always going to enter the lowest energy orbital available. Well, that is the rule or the principle. But with every good principle, there are good exceptions, and this is no exception. So atoms are more stable if they have a full sublevel. And remember, atoms want to become more stable. The next most stable arrangement, if they can't be full, it wants to be half full. That's the next best thing. So we have a couple of atoms, and they're going to be a little different than the pattern I taught you before on writing electron configurations. The first one is copper. If you write the electron configuration like I taught you before, on on copper, it would look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Well, what we have here is a sublevel that is not full or half full. So what's going to happen is these electrons here that are in the 4th energy level, one of them is going to drop back and go to the 3rd energy level. And so what you're going to end up with, instead of 4s2, 3d9 at the end, you're going to end up with 4s1, 3d10, because it's more stable this way. So copper's electron configuration actually looks like this, where you have that 4s1, 3d10. Now I have one that is a sublevel that is half full and one that is full, instead of one being full and one being not full, not half full. This is less stable, so its true electron configuration is with the 4s1 3d10. Next we have chromium. Try this one out, write its electron configuration like I taught you before, and then see, based on this pattern that we established with copper, if you can predict the electron configuration for chromium. You can pause this video cast to do that now. All right, the chromium is, as I taught you to do it before, its electron configuration looks like this. Again, we have a situation where this sublevel is not full and it's not half full. So it is not stable. So the atom is actually not going to have this electron configuration. An electron from the 4th energy level is going to drop down and go into the 5th energy level. So what we're going to end up with is this, where we have 4s1 and 3d5. Now, instead of having one sublevel full and one not full or half full, I have two that are half full. It is more stable, so that's why it has this electron configuration. Now, there are others on the periodic table that do not follow the off-bomb rule. In this class, we're going to pretend like they all do except for chromium and copper. So you need to know that the electron configurations for chromium and copper are different, and you need to know how they are different.